Hello everyone, my name is Dasin, and together with my teammate, we'll be presenting our team project for Artificial Neural Network course. Our project is about a problem that sounds simple, but it's surprisingly deep. Can we identify a language or even the accent of a speaker from just a few seconds of audio? But there's a more specific question behind our work, and it's the question that shaped the entire project. When we try to solve a task like this, what actually drives the performance? Is it the learning algorithm we choose, or is it how we present the data to the model? We designed the control experiment to answer exactly that. So here's how we present our project today. We'll start with the problem and why it matters, then talk about the dataset and the real obstacle we hit along the way. After that, I'll explain the two different ways we represented our audio data. And this part is really the heart of the project. Then Yunus will walk you through the three models we built, our numerical results, and the error analysis, and finally a live demonstration. And let's begin. So why does this problem matter? Identifying a spoken language or accent from a short clip is a long-standing challenge in speech processing. And it isn't just academic, it has real applications to it. Speech recognition systems that adapt to a speaker's accent work better. Call centers can route callers more intelligently. There are uses in forensic speaker analysis and a language learning app that give personalized pronunciation feedback. But as I said, our real interest was deeper, more scientific question. Look at the box on the right. This is the backbone of our whole project. When a model succeeds at this test, what is responsible for that? Option A, the learning algorithm we picked, and option B, the representation in which we feed the data to the model. These two factors are usually tangled together. If you just swap a simple model for a fancy deep learning model, and it does better, you can't tell why it did better. Was it the model or was it that the new model happened to use the data differently? To untangle them cleanly, we built a controlled three-stage experiment where we change only one thing at a time. I'll come back to the idea because it's the central of everything. So let's talk about our data. We use the Mozilla Common Voice corpus, which is a large open crowdsourced speech dataset. We choose three languages, Arabic, English, and French, and took 1,000 clips from each for a total of 3,000 labeled audio recordings. A few technical details that matter. We assemble every recording to a common rate of 22.05 kilohertz. This is important because later one of our presentations depend on time, and its different clips had different sampling rates. Their time frames wouldn't line up, so we standardized the first rate first. The typical clip is about 5 seconds long. Now, the box on the right is something I want to emphasize because it's a core principle we learned. Respect in the course, peer evaluation. We split the data 8% for training and 20% for testing using stratified sampling, meaning like each language is represented proportionally to both sets. And critically, all three of our models were evaluated on the exact same test set. We did this by splitting the data by indexes. So the specific clips that land in the test set are identical for every model that we test. So why does this matter so much? Because if each model saw a different test set, then any difference in their scores might just be luck or something else. One model got an easier test set by fixing the test set. We guarantee that when one model beats another, it's because of the model or the data, not by chance. So our data was huge. The whole Common Voice archive was enormous. So our first idea was, step one on the left, was simple, like download all the data for all three languages, process it, and then delete it. That immediately failed. We were working in Google Colab, which has roughly a 200 gigabyte estimate, and we believe right past it. So we tried step two, handle one language at a time, download it, process it, delete it, then move to the next one. This was a smarter idea, but we still hit the deck with it because even a single language's archive was too large for us to work on them, to sit on this while we worked through it. Just it just wasn't sustainable. So finally, step three, the solution was we built a streamlined streaming pipeline. So instead of downloading files to this, we process the data as it streams it. So on the fly and never write the audio to this at all. The archive flows through our code member by member. Each clip gets decoded and turned into features immediately, and then it's done. So with this approach, our disk usage dropped to nearly zero, and the problem disappeared completely. This wasn't in our original plan. It was something we figured out by hitting a wall twice. So now we get to the heart of the project. From each audio recording, in a single pass, we extract two parallel representations of the same sound. The difference between them is the whole point of our project, exactly. So let me explain both carefully. On the left is summary statistics vector. This is with four numbers. We compute features like the MFCCs, the male frequency septal coefficient, which describe the shape of the sound spectrum, the whole sound spectrum, along with the zero crossing rate, spectral roll-off, chroma, and energy. But here is the key. For each of these, we take statistics like the mean and standard deviation across the whole grid, and this is important. So we end up with one fixed setup with four numbers that summarizes the entire recording. And notice what it throws away. It discards all the information. It tells you the average character of the sound, but now how the sound evolved month to month. So on the right is the time series MFCC. Instead of averaging, we keep the MFCCs frame by frame for each sound, metrics of 200 time frames by 13 coefficient. If a clip is shorter, we pad it with zeros. If it's longer, we trim it to 216 frames, so everything has the same shape. The crucial difference is that this representation preserves how the audio changes over time. And here's why this matters so much for our test. Think about what actually makes an accent. Like, it's not static, it's average quality for someone's voice. Like, it's dynamic. It's how they glide from one vowel to another, the rhythm of their speech, the melody, like the timing, like all of the lives and time. The summary vector flattens it away. The time series representation keeps it. So the obvious question is, which one lets the model do better? So my teammate will tell you about everything. Will tell exactly these three models.
Thank you, Delphine. Hello, everyone. I'm Yunus, and I will take us through the rest. Before the medals, I want to share how to this project actually evolved because the final design wasn't where we started, and the story explains why the project is shaped the way it is. It began as a project my teammate started on his own using just XGBoost, a gradient boosting model, with the simple goal as of pushing the accuracy as high as possible. And but then we realized something important: XGBoost is not a neural network. It's an ensemble of decision trees, and for an artificial neural network course, a project with neural network in doesn't really fit. That realization is what pushed the whole project forward. So we added a 1D conventional neural network, a proper neural network, and here's where it got interesting when we fed that CNN, the summary data, it actually couldn't beat the XGBoost baseline. That was a surprising result, and instead of ignore it, we dug into it. And through research, and we learned that conventional networks really shine when they work on sequential time-based data, not flat summary statistic. That insight is what turned the project into what it is now, a controlled composition of three methods designed to isolate exactly what drives performance. And so the final form wasn't an accident, it came out a genuine process of discovery. including a result that confused us at first. And here's the overall system at a glance. Reading the diagram top to bottom, the data is downloaded as a stream. That is the pipeline that's been described. From a single decoding path, we extract the both representation, and then all the three models are trained and evolved on the same test sets. And we compare them with accuracy, classification report, and confusion matrices. And then the very bottom, there's a live demo. And but I want to draw your attention to the box on the right, and because it is the experimental logic that makes our conclusion valid. But Model 2 and 3 have a exact same architecture, the same layer and same training setup. The only thing we change between them is the input representation. This is a controlled experiment in the truest sense. When you hold everything constant except one variable, any difference in the outcomes can be attributed to the one variable. So if model 3 beats in model 2, it can only be because of the data representation and not the architecture. That was let us make a clean, honest claim at the end. And let me introduce the three models. Firstly, model 1 is an XGBoost, our baseline. It's a gradient boosting 3 ensemble that works on the 54 dimensional summary vector. One detail worth mentioning, and because a few audio how to say files got corrupted during the downloading, and our class size ended up slightly anarchical. To fix that, we used the technique called smooth, which generates synthetic samples for the smaller classes, but this is important for the fairness. We applied smooth only to the training set and never the test set. If synthetic data leak into the test set, the model would be evaluated partly on the fake data it helped to create, which would inflate the score artificially. That is what they call the data leakage, and avoiding it is the essential. And secondly, model 2 is a one-line CNN on the summary data. It used the same 54 numbers as XGBoost. Its entire purpose is to answer one question. One identical input does a neural network do better than the three baseline, and its architecture is kept identical to model 3. And finally, model 3 is our proposed model, a time series CNN. This one takes the 216 to 13 matrix, so its conventional filters slides along the time axis and learning the temporal pattern where accent actually lives. Same architecture as a model 2, only the input is different. And this is the architecture of our proposed model, and here's where a lot of what we learned on this course comes together. The network has three conventional blocks with the number of filters increasing 54, then the 128, and then 256. The idea which we covered in class, and it's that early layers learn simple local pattern, and deeper layer and combine those into more complex ones. After each block, we apply the batch normalization, which stabilizes and speeds up training by keeping the values in healthy range as they flow through the network. Then, instead of flattening the output, we used global average pooling. This means it was a deliberate choice. Flattening creates a huge number of parameters, and more parameters means the higher risk or higher parameters of overfitting, especially with a dataset our size. Global average pooling keeps the parameter count low, which makes the model more robust. We finished the 126 neuron dense layer and softmax output that turns everything into class probabilities. And on the right is our training protocol, and almost every item here is a concept from the course. We use the ADAM optimizer with learner grades 1.110. We set aside 15% of the training data as a validation set. And this is a distinction we learned to take seriously. The training set teaches the model, the validation set let us monitor is during the training to catch everything, and then the test set is touched the only very end the for the final. Honestly, actually, we use the early stopping with a patience of a 15 epochs, meaning if the validation loss stops improving for 15 epochs and training helps and we restore and the best weights so the model never overtrains into memorization. No overfitting. And a learning rate scheduler automatically helps the learning rate when the progress plateaus, letting the model settle more predictable. These are exactly the regularization and training techniques this course is about applied to the real problem. And the results we looked at overall accuracy. These are our most important slides. So let me walk through the three takeaways carefully. Firstly, and this surprised us, the CNN on summary data score 86.50%, which is the actually below XGBoost 89% of the. So this is the lazy assumption that a neural network always win. It's a simple false. With only 40 not 40, 54 aggregates feature and the modest amount of data, the tree-based model built-in assumption are actually a better fit for that kind of flat tabular data than a conventional network is. Secondly, and this is a key result. When we take the exact same CNN architecture and feed in the time series representation, instead accuracy jumps to 93.67%. It's a huge number. That's a 4.67 point improvement over the strong baseline. And remember, the architecture, the optimizer, the data split were all held fixed. So this chain can be attributed to one thing only, preserving the temporal structure of the area. Third, the model isn't just more accurate, it's also the most balanced. It's per class. F1 scores are all tightly clustered between 0.90, 0.92 and 0.96. So the headline of an R project is right here. Deceiver, deceiving the factor on this test is not a simple adapting deep learning. It's a preserving temporal structure in input. The data representation mattered more than the model class. When we came to error analyze, these are the confusion matrices, which shows us where the models make mistakes. Across all the three models, the most common confusion in the between English and French. That actually makes the linguistic sense within the corpus. The two languages are phonetical and rhythmical closer to each other. The either is the Arabic, and indeed Arabic is the easiest class through, reaching the 97% recall with our proposed model. But here's the satisfying part. Our time series model cut the total number of misclassification from the 66 for XGBoost and 81 for the summary CNN, all the way down to 38. And the biggest improvement happened precisely on that hardest English-French pair. This tells us that the temporal spectral pattern carry exactly the discriminative information that the summary statistics were throwing away. These are the learning curves. Blue is training, pink is the validation. For the neural network, the thing notice it's that the validation curves track the training curves closely. This is a healthy sign. It means the model are generally learning generalize the pattern, not just memorizing and the training data. If we're overfitting, you will see the validation curve flattening out of the get the worse while the training curve kept improving. And we don't see that. The dashed vertical line marks the batch effort chosen by early stopping. That's the point. Who's the weights we kept in? We kept it. So this slide is really the visual proof that the regulation tools we discussed, dropouts, it's a batch normalization, early stopping, are doing their jobs for the dataset of our size. And let me show you system in action. We built a web application with Gradio in our finally blog in code. Then the user can either record audio from the microphone or upload the file. Doesn't matter. Then they pick one the three models, the clip in the run through the exact the same processing chain the model used during the training, which matters because the model only works correctly and on data prepared the same way it was trained, and then it outputs the probability for each of the three languages. Let me bring it all together. We run a controlled the three-stage study of spoken language identification on Arabic, English, and French. By extracting both a summary statistic vector and a time series representation from the same recording and by keeping the architecture, the data split, and the training protocol fixed, we were able to isolate the one thing we care about, the effect of the input representation. And the results are clear. A CNN on summary statistic could not beat a well-tuned XGBoost 86.5 versus 889. But the same network, given the time series representation, reached 93.67% and nearly held and the error count. Because the architecture was held constant, that improvement came purely from the data representation. So our main finding in this for this text, the decisive factor is not the adoption of deep learning by itself. It's preserving the temporal structure in the input. Sometimes the right answer is not a bigger model. It's representing your data in a way that keeps the information that actually matters. For the future work, we would like to add audio data augmentation like noise and pitch shifting, try the recurrent or attention-based architecture on the top, the conventional front end. Use key-fold cross-validation for tighter confidence estimates and scale up to more language and the accent within the single language. Thank you all for all this and this our project. Thank you all very much your attention, and we will be happy to take any question. Thank you.